And welcome to our third CMPS to 11 revision session. This one is for the final. First, we'll be solving questions on time complexity because no one told me that he actually solved the log n question in the exam. I don't remember that anyone said that they actually were able to get it. So what I'll be doing is I'll be solving these time complexity questions that are not easy. That I actually got some of them wrong when I was doing this is actually from my CMPS 202 lab actually. So I got some of them wrong back then, and it's a really good practice. Okay, so now we have double sum equal to 0, int I equal to 0, int n equal to tab dot length. Okay, so what are we doing? We're doing n times, we're doing I++, so that's just basically O of n, right? So this one's easy. Let's go to the next one. Okay, so sort array, we have n equal to tab dot length. We have I and j. I min, okay, so I have I min auxiliary and I and j. As long as I is less than, okay, so I is less than n minus 1 and I++, and I don't see that they, okay, so sometimes they're changing I min, but they're not changing I, so here we have n operations, right? And then now min equal to tab. Okay, so we don't really have to understand what the code is doing actually, as long as we know the time complexity. We know that we'll be doing n operations, and each time in these n operations we'll be doing n minus I, right? From experience, actually, I can tell you that this is equivalent to n squared, because always when you're doing n thing, so it's like the summation of I from 0 till n almost, you see, because n times I'm doing I things, here I'm doing the reverse, I'm doing n minus I, but it's the same thing basically, maybe. So yeah, this is another n basically. Yeah, we don't need to understand the rest, so basically this is n squared. Okay, so now we have n, okay, and as long as I is, this is basically like a while loop, as long as I is less than n, int j equal to 0, j less than I, okay, so also as long as j less than n, less than I mean, it's similar to this, until now it's similar to this. Okay, so we're changing something, and then we're doing j++, and then we do I++. Okay, so this is also n squared, I don't see what has changed. Okay, so these ones are easier, so the ones that we've done up until now were easier. You can do the summations, but I like to just look at it and understand what's going on, because like when you're doing algorithms, maybe later on you'll not take out a pen and paper and do the summations, except if it's really complicated. Here it's somewhat clear, you see, and you could do the equations, and they're clear up until now, maybe. Okay. So now we have I equal to 1, S equal to 1, and while S is less than or equal to n. Okay, so we're going to do I++ and then S plus equal I. Okay, so this one's more complicated. So we have an integer n, and we have as long as S less than n. So you might think to yourself that, okay, this is O of n, but that's not true, because I'm not adding 1 to S, I'm adding I. So the first time I'll be adding 1, the second time I'll be adding 2, the third time I'll be adding 3, and so on and so forth. What is this equivalent to? Okay, so the first time I added 2, so the first time I did S++, and then I added 1, so the first time maybe I did S++. Actually, the first time I added 2, but it doesn't really matter, so I regard it as the first time is S++, and then S plus equal 2, and then S plus equal 3. So this will do this until we have S equal to n, or I mean S greater than n. So what is this equivalent to? You can directly see that this is very fast. This algorithm is very fast. Why? Because we're doing instead of doing S++, we're doing S plus equals a number, and this number is increasing. So like if it takes 5 operations, we didn't do S plus equal 5. What we actually did is S plus equal 1 plus 2 plus 3. So we did S plus equal n squared almost. So O of n squared, right? So the thing that we're adding is an O of n squared instead of being an O of n. So it will take way less time to halt. Let's start to do this one mathematically. Okay, so if you have S equal to 1 up until n, okay, so no. Okay, so let's think about this for a second. So what we're doing is s plus plus and then, okay, so this mathematically is equal to what? This mathematically is equivalent to s plus plus n into n minus 1 over 2 equal okay, so this, let's regard this as k, okay, because if we do like 5 operations, we're going to, if we do 5 operations, we'd have done the summation from I equal to 1 up until 5 of I, right? That's the thing that's added to s. So this is what we want to be added to s, so that we want to know how many operations we'll do, right? And then each operation, like, so if we do 5 operations, we'd be left with k equal to 5 in this, right? So we want to know how many operations we're going to do up until s is equal to n, right? Actually it's up until x is greater than n, but it doesn't really matter maybe. So we have this. Now what can we do? So we have n minus s, okay, so but s is 1, so yeah, so we can get rid of s, and then we'd be left with this, because s is a constant, we can get rid of it, and 2 is a constant, we can get rid of it, and the minus 1 is a constant, we can get rid of it. We'd be left with k squared equal to n, right? So the number of operations is n square root n, right? And I believe this is the answer. So yeah, they did the same thing basically, maybe. It does belong to O of n, because radical n, square root of n does less than n, but I believe here they made a mistake, they meant to write radical n. Okay, so now int I equal to 1, count equal to 0. For I equal to 1, I times I, okay. So we're doing I times I, and I plus plus, we want I to be to remain less than n, right? Okay, so I'll disregard the I plus plus, because the I times I is way bigger than the I plus plus, right? Oh no, sorry. So they're not doing I times I, they're doing I times I is less than n, but they're still doing I plus plus, right? So I times I is less than n. If I times I is less than n, then I is less than square root of n, then it's of square root of n. This one's easy, maybe, right? Okay, so let's see. We have, okay, some of you would look at this, would see 3 nested for loops, they'd say n cubed directly. Let's see, but that's not always the case. We have I equal to n over 2, I less than, okay, so this is of n. But then the next for loop is from j equal to 1, okay, and we want j plus n over 2, okay, so this is the same as saying that j is less than n over 2 almost, something like that. Okay, so that's also n things, and we're doing n plus plus, so that's also of n. Okay, but here the k is where it gets tricky, right? Because k, we're doing k equal to 1, k less than n, but then k equal to k times 2, so that's log k, so that's n squared log n. I mean, this is log n, not okay, so the last one is log n, right? So yeah, we'd have n squared log n as a total, because the last one is log n, and count doesn't really matter in the entire thing. Yeah, so it's n squared log n. O of n squared log n. Okay, so now what? Okay, so we have here also 3 for loops. Again, not necessarily n cubed, not necessarily n squared log n. We'll see what it is. Okay, so the first one is still the same. It's O of n unless I is changed here, but I is not changed anywhere else, so it's O of n. And then the next one we have now we have log n, because okay. And in the third one we have another log n, so it's n log squared n. Okay, so this also is right. Now what do we have? We still have a bit more actually. Okay, the harder ones maybe are yet to come. Okay, so first we have here a for loop that's O of n, then we have another one that's also O of n, right? Okay, is there anything else? No, just I believe that this is just n squared, because we have I less than, yeah, I believe that this is just n squared. Let's see. Oh, there's a break. I didn't see the break. Okay. I was wondering why would they put something as easy as this. Okay, so I didn't see a break. It's important to see the code. I was just looking for things that multiply I and j. So yeah, since there's a break, so we'll n times, you'd be going into this n times supposedly, but actually what you'd be doing is you'd be going, okay, so you'd be going into the first one, into this n times, but each time the for loop would break directly, so you'd only be going to this n times, but into this only once each time. So yeah, so now, okay, so this one is similar to the one before. This is okay, so if you remember the time before when we did j plus equal I, we said, okay, so the first time is plus 1, then plus 2, then plus 3, so it would be square root n. Here it's not just like that, maybe it's similar, but maybe not the same, because here you're doing n times this, okay? So the first time I'll always be doing j plus 1, and then the second time I'll always doing j plus 2, right? And the third time, okay, some of you would think that this is n squared, right? Because, so it's always doing of n operations. But that might not be true, because amortized it might be way better, right? Because there's one time that it only enters once. We know that, you know. So let's try to think about this. So first we have one loop that does of n, so when I equal to 1, and then the next one does n over 2, and then the third one does n over 3, and then like this up until 1, right? So this is the number of operations that we'll be doing. So this is the number of operations that we will be doing. So this is equivalent to what? This is equivalent to n to summation 1 over I equal 2 to up until n, right? This is I. So this is equal to n times this summation. What do we know it to be? We know it to be log n, maybe. This would be n log n, if I'm not mistaken. Let me make sure. I think they have here the series. Okay, so the summation of 1 over k for k is equal to log n. Okay. And this one's right too. Actually, something nice in O, in big O, and in asymptotic time complexity in general, it doesn't matter the base of the log. You can say, like, it could be log base 2 of n, and you write log base 10 of n, and it doesn't matter. You can think about this if you want. Okay, so here. Okay, so let's go over these very quickly. Okay, so now here we have int I equal 1, I less than n, I plus plus, result equal to this, and then we're doing result. Okay, so result doesn't matter really here, because result doesn't affect the loops. If you want, the result is just something that we're calculating, right? So now, what can we see? We can see that here there's n operations, because I is not modified inside, and here we're just doing I plus plus. And then if this, then we'll be going into the second for loop. But always when you're calculating time complexity, you take the worst case. So you assume that you'll always be doing this, because this is O of n, but this is O of 1. So you'll always assume the worst case, that you will be doing O of n, so this will just be O of n squared. Okay, so now let's go ahead and solve this problem. Okay, so here we have the first one. We're doing k times equal to, right? So that's log n directly, because we're not doing anything to k inside. And then the one after that, we're doing I plus plus, and I is less than k. Okay, so if we know that I is less than k, some of you would be tempted to say that this is and k is less than n. Some of you would be tempted to say that this is O of n. That's not really true, because that might not be true. Why? Because we have ones that it's of once n, one time it will be n, and then the other time it will be n over 2, and then the other time will be n over 4, right? Because k we're multiplying it by 2. So the final time it will be n operations. The one before that will be n over 2, right? So it's not very right to say that it's O of n. And then here we have two operations. One of them would be O of n, and then the other one would be log n. Some of you would multiply these two by mistake. You don't have to multiply these two. What we know here, that one of them is greater, which is the O of n, is greater than the log n. So that's the only one that's important. So this one doesn't really matter, because whatever this comes up to be, it will be multiplied by O of n plus O of log n. So O of n plus O of log n will be left with two terms, and one of them will be larger, which is the one with the O of n, right? So here we can substitute this entire block with O of n. Okay, now what do we have? Now we'll be doing summation. Okay, so this one it would be maybe harder to think about it in your mind. You'd have to write the summation maybe, but we have the summation from 1. So we have log n of times. What am I doing? Each time I'm doing okay, so each time I'm doing from I equal to 1, I'll write I as j because I wrote k I instead of k. Okay, so we'll be doing from j equal to 0 up until I operations, right? Okay, and then we'll be doing n inside, so I'll put n outside, and then we'll be left with a summation from I equal to 1 up until log n of the summation of from j equal to 0 to I, right? And that's just in the order of I squared. It's I into I plus 1 over 2 maybe, right? So it's the order of I squared doesn't really matter. Maybe I can directly write I squared. Okay, so now what? Now we're left with summation from I equal to 1 up until log n of I squared, right? Okay, so what's this summation? Okay, so actually here I made a mistake. It's not each time. Okay, so here I said number of operations, right? So we're doing log n operations. But then, okay, so let me redo it. Let me redo this one. Okay. So what we're doing is we're doing. Okay, so here what are we doing? Here what we're doing is we're doing log n operations, right? So here what we're actually doing is we have here log n times. We'll be doing the first time I'll be doing how many operations? So the first time I'll be doing 1 operation, and then the second time I'll be doing 2 operations, and I'll be doing 4 operations, right? Up until the time that I do n operations. Okay. So the k, this holds in log n, right? The one that's outside, because I'll be doing this log n times. So this will be log n. Okay, but what we'll actually be doing is, right, it's right that we're doing from I equal to 1 till I equal to log n, but each time I'll be doing 2 power I operations, right? Or from I equal to 0. And then this entire thing will be times the thing that's inside, so something plus something, which we said will be equate to O of n. So we'll have O of n outside, and then here what we'll be left with is n squared. Okay. And there's a formula to do this maybe. You might be able to see it, right? Because 2 power log n is n. And then, but who says that the other things are not, that the other things will not make it maybe n squared or something? But I believe like there's a math formula for this. I've actually just memorized it, you know. But you can look it up. Maybe they gave it to them here in the tables actually. Okay, so here they have this. Maybe okay. So the geometric sum, is it the same thing though? So okay, yeah, it's the same as geometric sum. I haven't done these things from a while, but yeah, it's O of n squared. Okay, so now for the last one. Okay, so the last one. Okay, so this one's log n, right? It's like multiplying by 2 is the same as dividing by 2. If you start from O of n, so if you start from n and then divide by 2, it's the same as multiplying by 2. And then what we'll be doing is log n times each time. So j doesn't have anything to do with I, so it will also be log n. So that's log squared n. And then also this is okay. So that's n log squared n, I believe, because the last one will be doing n operations. You know, plus equal to or plus equal 1,000. This is the same. It's all n operations. So yeah, this is it. And now I'll be solving a induction question of my own that I think you might like. It's different than the things that you've been taking in class. It's really interesting. Okay, so now I'll tell you to prove that any number that can be written as the sum of n consecutive numbers is equal to, or can be written as, okay, so any number that can be written as the sum of n consecutive numbers means, like, if I say n equal to 4, then like 1 plus 2 plus 3 plus 4 is a valid number of this sort, or like maybe 6 plus 5 plus 4 plus 3, maybe like any n consecutive, the sum of any number that's equivalent to the sum of n consecutive numbers would be a number that we are interested in, right? So any number of this sort, you have to prove that it can be written as n into n plus 1 over 2 plus n times k, where k is some positive integer. Okay, so how can we do this? Okay, so first let's take a look. It looks like an induction question, right? Why does it look like an induction question? Because 1 plus 2 plus 3 plus 4, and then I have 2 plus 3 plus 4 plus 5, and then I have 3 plus 4 plus 5 plus 6, right? So it looks like an induction question. So if I can solve it for the base case, okay, so this for n equal to 4, if I can solve this for the base case, I can solve it for anything, right? And actually the weird thing here is that n is not of interest, right? So our base case is not when n equal to 0, because saying that n is equal to 0 is saying that if it can be solved for all numbers, or like saying that n is equal, let's say 3, and then going from there, it's like you're saying if it can be solved for all numbers that can be written as the sum of 3 consecutive numbers, then it can be written, then can be solved for all numbers that can be written as the sum of 4 consecutive numbers. That's not what we want, actually. You'll see here how we'll be solving it. What we'll be saying is, for the number that is equal to the sum of the first n consecutive numbers, this number is equal to what? It's equal to the summation of I equal 1 till n, right? Of 1, because you're doing of I, because you're doing 1 plus 2 plus 3, right? N times. So you're doing this n times, that's n into n plus 1 over 2, right? Or like so of n squared, right? Actually here we're not no longer doing time complexity, so the 1 doesn't matter, but right, yeah. So it's n into n plus 1 over 2. So now we want to prove it for the number that is the sum of the next n consecutive numbers. So we're removing 1 and we're adding n plus 1, right? So that number would be equal to n into n plus 1 over 2 minus 1 plus n plus 1, right? So this is what? This is plus n. Okay? So, and then you'd prove it here like this in the inductive step. So you'd say that the one that's the sum of the second largest, and then the third largest, it will be the same plus 2n. So each time we're adding n. How can we see this actually? Actually, when I came up with this question, I didn't really think about it in this way exactly. What I was doing was I said, okay, so 1 plus 2 plus 3 plus 4 maybe. This is equal to what? This is equal to 10, right? And then 2 plus 3 plus 4 plus 5. This is equal to what? This is equal to 14, right? Because 2 I had this 5, this 5, this 4. So this is 14. So this is actually how I came up with this. Okay, I looked at it. Okay, so I saw that each time I'm adding plus 4. So I said, so the first one is equal to n into n plus 1 over 2. And then whatever if I look at the one that's after it, the number that's is the sum of n consecutive numbers that's directly greater than the first one, it will be greater than it by 4. And the one greater than that directly, it will be greater than it by 4. So between any two, there's plus 4, right? So any number will be the same, the first one plus some multiple of 4. So it will be n into n plus 1 over 2 plus k times n, because like 4 is k in this case, right? I hope you find this session useful, because actually I have final like directly after I solve the session. I have final that I have to go to do, so I don't have a lot of time to prepare questions and to come up with new ones. But this induction question I found to be very interesting. I found that it's not the same way that you usually do induction, and it makes you understand the concept of induction better. Good luck with your final, and hopefully we'll be recording more sessions in the upcoming semester.